Hello viewers, my name is Damilari. In this lesson we'll be looking at the topic, the periodic table. To start with, what is periodic table? This is a table that is showing us the classification of elements, or you say arrangement of elements, based on groups, that's vertical, and period, that's horizontal. Then the next thing, from the history of periodic table, we have some scientists that talked about periodic table, one of which was Newland. He explains periodic table based on arrangement of elements in octaves. Octaves means 8. That means elements of 8. Just like if you can see this periodic table here, there are 8 from here to here. They have 8 groups, so that's why he called it octaves. So Newland, you can remember with NO. Newland explained based on octaves. Then another person was Lavoisier. You can use LMN. M is metal, N is non-metal, meaning that elements are arranged based on metals and non-metals. If you look at, there is a particular periodic table from this picture here showing us the complete elements. As you can see here, that some elements are here from hydrogen down to the last element here. They are 118 in numbers, though from this drawing is not up to 118, but this space, if you include these spaces here, it will make it 118. That's after 109. Then we have 110, 111, 112, 113, 114, 115, 116, 117, 118. So that tells us that we have 118 elements. Now, what am I bringing up from what Lavoisier said? He said we will see metals. What are the metals? Lithium, beryllium, sodium, magnesium, potassium, calcium, all these elements on the left like this. By the time you come down to this, aluminium is still a metal. You come down like this and start going along this boundary. So they are all metals to the left, but to the right you'll be seeing non-metals. But apart from boron, silicon, these ones here, they are metalloid. That means acting as metal and non-metal. So they are the boundary between the metals on the left and the non-metals on the right. So back to what we're saying about Lavoisier. So he was classifying the element based on metals and non-metals. Then another person was Mendeleev, Dmitry Mendeleev. Dmitry, the letter D of that Dmitry Mendeleev, it means he was one that designed the periodic table, and he left gaps when he was designing them, just like the way these gaps are. He left spaces for some elements that are yet to be discovered. So, and again, he gave a law, we call it periodic law, which was based on relative atomic mass. He said elements are arranged based on their relative atomic masses. Not until mostly in 1914 now stated that same law, that it should be based on atomic numbers, not based on relative atomic mass. So what is now that law? The periodic law states that the properties of elements, they are functions of their atomic numbers, meaning the atomic numbers will determine the property of elements. Just like someone that is 1 year old is a 1 year old baby compared to someone that is 20 years old. So their properties, their behavior will be different. Just like hydrogen also, that is number 1, is a light gas compared to chlorine, number 17, which is heavy gas. So the same way we can use it to remember periodic law. Another thing is electronic configuration. Elements on the periodic tables, they are configured electronically. As you can see, hydrogen 1s1, helium 1s2, lithium they put 2s1, and so on. All these are called electronic configuration. How did they arrive at them? Like what Hofbauer said, Hofbauer principle, AUFBAU. He said we can write 1 to 8 putting SSS, write 2 to 7 putting PPP, 3 to 6 DDD, then 4 and 5 F. That means SPDF. They call it blocks: block S, block P, block D, and block F. As you can see from this table here, I said this is our S block. the group 1 and 2 are S block, so that's why you see these two there. Then P block, they are 6 from boron, 1 2 3 4 5 6, so these 6 represent P block. Then D, they are 10 from scandium to zinc, they are 10. Then the last one for F, they are 14 from this point to this point, they are 14. How will you remember? Just start with S, that is 2, plus 4, that is 6, plus 4, that's 10, plus 4, that's 14. So these are the blocks, and that's why as we start writing the electronic configuration, anywhere you see S, the highest must be 2, anywhere you see P, the highest must be 6, and so on. So back to what we're saying here, that how did they arrive at this electronic configuration of all this 1s, 1 2s, 1s2, and so on. I said use this off-bar principle, learn how to draw 1 to 8, 2 to 7, and so on, then put SPDF there. Then if you want to know configuration of each element, like hydrogen of number 1, just pick the first thing you see here, 1s, so you write your 1s, and because hydrogen has 1, you put 1 on top. If you want to do helium number 2, you still pick that same 1s, this is the 1s, and put 2 on top, because the highest of s is 2 from what I showed. By the time you move to lithium, lithium has crossed to number 3, but don't forget from 1s, highest of s is 2, so the remaining one will now come to the 2s, and that's why they put the last thing, the remaining one, that 2s1, it was written here, so they left the 1s2. Then if you move to beryllium 4, meaning that you give 2 to the 1s, another 2 to the 2s, so it's the second 2 that is written here as 2s2. By the time you move to boron number 5, you give 2 to s here, 2 to another s, making 4, then 1 to the 2p. So we are selecting only the 2s and 2p written here. So why are we selecting that, leaving the 1s? The reason why we are selecting only the 2s, 2p is because we need the 2 for the period 2. So meaning that every last orbital here, or energy level, so is what will determine our period. So you can see here 2 2, the last one 2 2 2 2, so it shows that they are in period 2. But this one 1 1, they are in period 1. Then 3, you can see 3 3 3, the last one, so every 3 here shows that they are in period 3. When you come here 4 4, they are in period 4. So that shows that what elements are arranged on the periodic table based on periods. So then another thing about this period, though we'll still talk about it later, is that in period they will be on the same shell. That means this one on 1 shell, this one on 2 shells, on 3 shells, on 4 shells, so they will have the same shell. That's for period. But when it comes to group, they will be on different shells, but they will have the same valency. Like all these ones now, they have valency 1. That means number of electrons at the outermost shell, they are always 1 1 1. This one, they are always 2 2 2, and that's why they are in group 2. This one, they have valency of 3. Just plus the 2 numbers here, 2 plus 1 3, plus the 2 number here, 2 plus 2 4, so valency of 4, and so on. So telling us that what they arrange the element based on valencies and based on their shells. So that is, now back to this, we have seen how they derive this configuration, but take note from what I wrote here that the last 2 energy levels are the focus. These last 2 energy levels, they are the ones that we selected. If you want to know the group, like this one now, 2 plus 6 8, means that it belongs to group 8. Then another one, the last one, picking the last one for period, that means these 2 pieces, we pick the 2 for the period. So that is what we have here. Now let's move to the basic features of the group. So looking at the groups, what can we say about the groups? Elements in the same vertical. So when you are looking down vertically like this, that is group. But if you are looking at this at it like this in form of horizontal, that is period. So anything vertical represent groups, and they are 8 in numbers, group 1 to group 8. The 8 is also called group 0. Why? Because group 0, they are unreactive, they are rare gases, they are noble, they don't used to react. When the positive ones are on the left, that means the metals. Remember from what I showed you on the periodic table here, that when you cross along this boundary, boron, like this, like zigzag, so when you cross those ones on the left here, you see them as metals, they always give them plus. Then those ones on the right here, they are non-metals, they give them minus. But the middle one is the metalloid. And take note, if you want to take your minus from the end here, you start from 0, the last one 0, then the next one will carry -1 when it comes to oxidation number. So -1, -2, -3, so that's their oxidation number. But when it comes to valency, if this one is 0 from oxidation number, is also 0 for valency. If this one is -1 from oxidation number, it will be 1 for valency. If this one is -2 from oxidation number, it will be 2 for valency. If this one is -3 from oxidation number, it will be 3 for valency. Why this one is 4? But the remaining ones, they are just positive. That means if this one is +1, oxidation number, valency is 1, +2, oxidation number, valency is 2, +3, oxidation number, valency is 3. So that is how they are arranged. And even looking at all those +1, +2 I was reading, they can also use it to form a compound. For example, magnesium that is +2 can join with chlorine that is -1. So since magnesium is +2 and chlorine is -1, they are not yet balanced. So that's why if this one is 2, the 1 of chlorine will make chlorine appear twice, and that's why you see MgCl2. MgCl2. So telling us that we can also use it to form a compound. And also they still use the same periodic table when naming a large compound, like to know the middle name. When I say middle name, like carbonate, hydrogen triazocarbonate 4, you can use carbonate to know that okay, it's in group 4 because this is 1, 2, 3, 4. Nitrate, you can hear nitrate 5, so that this one is in number 5. So you can hear sulfate 6 from group 6, so and so on. So meaning that we can use this periodic table to do a lot of things. And also looking at this same particular transition, they call this one transition metals, the D block. So they are majorly metals, they are colored. So most of them are colored elements. So that is still part of the periodic table, though we can't exhaust everything here, but just to brief on the periodic table. So here we have seen the Hofbauer principle telling us about the configuration here. Then in addition to that, take note, as I said, highest of S is 2, P is 6, D is 10, F is 14. So in case you are told to write the configuration of, let's say, that of calcium of number 20. Remember, calcium is the last element from the first 20 elements, 20. So if you are told to write the electronic configuration, you see 1s2 from this line here, the highest is 2, then 2s2 from here, then 2p6, because highest of 2 is P is 6, but take it diagonally, 1s, 2s, 2p before 3s, 3p before 4s, 3d before 4p before 5s. So that's how these things are arranged. So just be putting 2 for s, 2 for s, 6 for p, 2 for s, 6 for p, 2 for x. So use it to get electronic configuration. So but once it comes to a higher number like zinc of 30, it means by the time you reach the P, the next thing you move to D, which is highest of 10, 3D 10. But take note of something here, that there are some elements like chromium and copper, those ones that are close to 30, close to 25, that when writing their configuration, you are going to take out of the S and give it to D. For example, while writing chromium, after you have taken the 4s2 for calcium, normally it should remain 3d10. So 3d10 to make it 30. But if you are dealing with chromium, so it means you just say 3d4. But instead of writing the 3d4, we'll take 1 out of the 4s2, give it to the 3d4, to turn to 3d5, while this one will remain 4s1. The same thing when you want to do that of copper 29, you see after 4s2, instead of 3d9, we'll turn the 3d9 to 3d10, while 4s will become 4s1. So these are commonly as in WAEC. So let's proceed as we still look at more explanation of periodic table. Now as we come down here, we have said groups, they are vertical and they are 8. Then another point is that from the same group you will see the same valency from what I've said earlier. Another point is there's an exception for group 0 elements, where I said those ones they are rare gases, so that's why they always give them 0, so they belong to group 0. Then the next point is there are some family names they give to each group, like group 1 they call them alkali metals, group 2 alkali earth metals, group 3 boron family, group 4 carbon family, group 5. That means using the first element to name the family. Like I said, this one alkali metals. And why? Because alkali means base, meaning that we can use this metal to form a base. Then this one alkaline earth metal, also base, we use it to form a base. Once you take OH, add OH to the metal, it will turn to base, like sodium hydroxide, magnesium hydroxide, so they will form a base. So these are the alkaline earth metals. Then by the time you come here, boron family, carbon family, nitrogen family, using the phosphorus element, oxygen family, but this one is halogen, they are salt formers, they can form salts. Like if I add sodium to chlorine, sodium chloride, that's salt. Then these ones are the rare gases. So these are their family names, and I've said these ones are transition metals. Then if you come down here, these are the lanthanides and the actinides, so that's their family names. So back to what we're talking about here. So we said they have family names. Then another thing, we move to period. We have seen groups, so that groups are the vertical ones, all these ones are vertical group. But we want to look at periods. So the way we have 8 groups, that's from 0 year, from 1 year down to 8, that's 8 groups. So the same way we have periods. So let's see how many periods we have. There are 7 from here, period 1, period 2 down to period 7. So we have 7 periods. So what are we saying about periods from here? So we're told that periods, they are horizontal, so they are on the same horizontal, they are in the row. So horizontal, that's our period. Then they always have the same number of shells. So I've said that earlier. This is just the notes that will help you to know the period. So I'm always looking at the last energy level. The number that is there will tell us the period it belongs to. Like if you are told, okay, what period does these elements with this configuration belong to, just check the last number, that's the period. So because each of them has a shell, K shell, L shell, M shell, so that's period 3. So then the next one, we have another period here as example, maybe period 1. So having n equal to 1, that's for all those maybe hydrogen and helium. So they have period, they belong to period 1, and that's why you see 1s2, 1s1, because they belong to 1. But period 2, you'll be seeing 2s joining with it. So that's why for lithium you see 2s in it, so because it belongs to period 2. So all these I've explained earlier just to remind you of what the periods is talking about. Now I want to quickly look at some questions that are under this topic. So we have mentioned 2 criteria used for placing an element. That means when you are arranging elements, what are the things you consider? You consider valency. So like those ones that have the same valency, they will be on the same group. Then we also consider their shells. Those ones that are having the same shell, they will be on the same period. So then the next question, the electronic configuration of X is this. What is the atomic number? So if you want to know the atomic number of this element, just plus the numbers that are on top, the superscript, 2 plus 2, 4 plus 6, 10, then plus 2, 12, plus 6, 18, plus 1, 19. So the atomic number is 19. If you are told to state the period, what period does this X belong to? So to get the period, just look at the last number here, which is what, 4. So the period is 4. Then if you are told to give the number of valence electrons in this element, so the number of electron, it has just 1 valence electron. So how do we know? Just look at the last number that is at the top here, so that's the valence electron. It has 1 valence electron. The name of this element X, so being element of that is having atomic number of 19, that's potassium. So potassium is one that has 19. So there are still many questions, though we can't be answering them now. Let's just move straight to blocks. There are blocks of elements. Blocks will comprise 2 or more groups, or two or more groups. So when you take group 1 and group 2, that's S block. When you take group 3 to group 8, that's P block. Then in between group 2 and group 3, we have what we call transition metals, which is the D block. So D block is in between. So as you can see from the drawing here, so in between this group 2 and group 3, we have the D block. Then the F block, so they are coming from this place, that's from period 7 and period 6 and period 7. That's where we have the F block. As you can see from this place here, this is number 57 instead of 58 here, so they brought the 58 down here, meaning that it's coming from period 6. Then after 89 here, instead of 90, they brought the 90 down here, so mean that from period 6 and 7 we are able to get our F block. So now back to what we're looking at here, is the blocks. So blocks, talking about group of when you have many groups, 2 or more groups. So S block has 2 groups, so that's group 1 and group 2. So an example of element that under S block, like lithium, and that's why you see SSS. So it's mostly it ends with S. It ends with S. Then P block, so those ones, there are 6 groups that belong to it. So group 3 to group 0, so they are the P blocks. And from this P, if you now merge the first two things I've talked about, the S block and the P block, both of them, we call them representative elements. That means they are from the first 20 elements that represent the periodic table. So then we also have noble elements. Those ones that are the last group, they are the noble element. Then the D block, I've talked about transition metals. Then the F block, the lanthanides and the actinides. So then in addition to that, we still have some questions, revision questions here, so which you can also use to test your knowledge of periodic table. So they can ask what are representative elements, that's the S and the P. The S and the P, that's from what we have, the S and P block, they are representative. Why? Because they are from the first 20 elements. And two examples like hydrogen, helium, any elements you know from the periodic first 20 elements. The X is an element with a valency electron of 2. Which of following elements will be in the same group in this periodic table as X? So since they said electron of 2, valence electron of 2, just go straight to this. The one that has atomic number of 12, it has valency of 2, because if you pick what we call 2 and 8, the remaining will be 2. But others, 2 and 8, the remaining will be 3, 2 and 8, the remaining will be 7. So all these ones are not having 2 after picking 2 and 8. So meaning that S is the one that has the same valence electron or the same group as X. Then if you look at the next question, consider the following element represented thus. So A, B, C, D, E. So having this atomic number of 3, of 8, 12, 18 and 19. They say state which of the following is a noble gas. A noble gas, we have a complete shell after taking your 2 8s. So 2 8, that's making 10. So from the noble gas, it shows that the last one, those ones that belong to the last one, for example, here we have 18. So this D will be the correct answer, because 2 plus 8 is 10 plus another 8, that's 18. So this D is a noble gas. Then the one that is an alkaline earth metal, alkaline earth metal, that means those ones that are in group 2, so like this 12, after 2 8 you see 2. Then the one that belong to group 2, that same B, then belong to the S block. So those ones that are S block, they are in group 1 and group 2. So how will you know group 1 and group 2? Just like this one here is number 3, so mean that it will belong to S block, because 3 here, once you remove your 2, it will remain 1. Then for this 8, once you remove your 2, it will remain 6, so it does not belong. This one, once you remove your 2 and 8 is remaining 2, it belongs to S block. Then this one, 2 8 10, 2 8 is 10, the remaining 8, it will be at the end, so it does not belong. So and so on. That's how to know the group they belong to. Yes, the group and the block. Then the one that belong to the same group, so still related to all I've said from the previous one. So there are still a lot of questions here that you can also try to solve. So but I just want to quickly summarize all those ones there. Now let's still get more points from another textbook here. So the first one we looked at is from a particular textbook, but this is another textbook again. So from here we have seen the real drawing of periodic table, and as you can see the zigzag, that means the zigzag here is just to show you that those things on the left are metals, those ones on the right are non-metals, apart from the one that is along the boundary, which are metalloid. These are the metalloids. So this is the periodic table, so helping you to remember how the drawing is. Then the last textbook here, so we'll also use it to answer some questions on the periodic table. So we just want to answer true or false. So here the first question here, they said the modern periodic table of elements was based on the periodic law of Mendeleev. Is it true or false? As you can see here, they say it is false. So because here they are saying Mendeleev was explaining periodic table, the modern periodic table of elements. They said it was based on the periodic law of Mendel. No, it was not modern. The modern was by Moseley. Moseley was the one that talked about atomic number, but Mendeleev talked about relative atomic mass, so it should be false. So then the second one, number that's alphabet B. The element with atomic number 12 belongs to period 3 of the periodic table. Is it true or false? So from what we have here, it is true. So meaning that the maximum principal quantum number in the electronic configuration of the elements gives the period to which the element belongs in this case. So the electronic configuration is this. So hence the period is actually 3. So meaning from the second question here, saying the element with atomic number 12 belongs to period 3. So it actually belongs to period 3. And how will you know? So like I said, break the 12. When you break the 12, as it is broken here in the electronic configuration, 1s2, 2s2, 2p6, 3s1. So it belongs to period 3 because the last number here is 3. So that's why we say it belongs to period 3. So it is true. Then let's move to C. So from C we have helium. Helium is not a member of the noble gases because it has 2 electrons in its outer shell. So let's check the answer here. So it is false. It is false. When they say helium is not a member of noble gas, so that's false. It's actually a member of noble gas, because looking at helium 1s2, remember helium is number 2, so 1s2, it is a noble gas because the orbital in the only shell available and also the outer shell is filled. Remember that the highest of the 4 shell must be 2, and since it has occupied, it has filled it, so that's noble gas. So noble gas have filled electrons. They always have filled electrons in their shell, so meaning that the 2 has completed the duplet. They call it duplet, so it's actually a noble gas. So that leads us to D. So what do we have in the elements in the same period have the same number of electronic shells? Yes, elements in the same period have the same number of electronic shells, so that's true. So from what I explained earlier, that when you look at each element, each period, those ones that are in period 2, they will have 2 shells. Those ones that are in period 3, so once they are in the same period, they will have the same shells. Then the next one here, that's E for alphabet E. Elements in the same period, they said they have similar chemical properties because they have the same number of valence electrons. No. So from here, which is E, we can say false. Elements in the same period, they don't have the same valency. No, their valency is not the same. It's the one in the group that has the same valency. So hence different chemical properties. So it's different chemical property you will see there because their valence electrons are not the same. Assuming it's group they have the same valence electrons, so they can have similar chemical property, but this one, their chemical properties are different because their valence electrons are also different. Then a period 2 to 7 begins with alkali metal atom having only one valence electron, and they are ending with a noble gas atom having a complete outer shell. So let's move to alphabet F question. So F says all the elements whose atoms have completely filled sublevels in the outer shell belong to group 0. Yes, so that's actually correct. So for F, so we see it as true. So because they are complete, anything complete is in the last group filled. So then alphabet G, the number of electronic shells increases down any group of the periodic table. Yes, so the shells are increasing as you are going down. So that's for G. So from G here, alphabet H, then alphabet G, alphabet I. So from alphabet I, we say it is true, meaning that you are going down the group. So sorry, okay, this is the G. So as you are going down the group, there is addition of successive shells. The shells will be increasing. So and this results in the increase in the number of electronic shells progressively down a group. So then we move to alphabet H. H says elements in the same group do not have similar chemical properties. That's false. So that's actually false. So here, elements in the same group, they should have the same number of valence electrons, so they should also have similar chemical properties. So then moving to I. In I, prior to 1984, the main groups were designated as A, while the subgroups of the transition elements were designated as B. So for alphabet I, that's true. So looking at the I, they said in 1984 the main groups, so they call them A, while the subgroups of the transition elements, they are the B. As you can see from this drawing here, so we have the A. Okay, that should be from the first drawing, from the first textbook we're using here. So we can see that they have A as the main group. So here, so all these ones here, they are the A. So these first 20 elements, they are the A. But by the time you look at another periodic table, so the one that has a complete table, so that one shows us the B. That means where the transition metals are. So look at these ones that are on top, they are the A, while those ones that are down here, they are the B. So let's go back to where we are answering our questions. So from what they said earlier, that the A and the B, sorry, let me try to open the question back. Okay, so from the where we stopped, I, prior to 1984, the main groups, all those groups, they were designated as A. That means all those group 1, group 2 down to group 8, they are A. But the subgroups of the transition elements, so those ones that are below, so they are the designated as B. Then the last question here, which is, okay, we still have J and K. Okay, so the JKL, so the JKL, they are the last questions under this topic. So for the J, the elements with the atomic numbers 20 and 21 belong to S block and P block respectively. So that means, is it true that element that the atomic numbers is 20 and the one that is 21, is it true that they belong to S and P block? So let's confirm that for J. So for J is false, because the differentiating electron for the atom of the element with atomic number 20 is accommodated by the orbital of the 4s sublevel, while that of the atom of the element with atomic number 21 is in one of the degenerated orbitals of the 3d sublevel. So hence the element belongs to S and D blocks. So it means, and this is the drawing that will prove that statement. So that looking at the one of number 20, calcium, it belongs to S block, but the next one, number 21, scandium, belongs to D block, not P that is here. So that is to back up that point. So then the next one after our J, K says boron belongs to the P block because its differentiating electron is accommodated by a p orbital. So looking at K from the answer here, we say it's true. Boron has 1s2 2s2 2p1 because it belongs to number 5. So it has the differentiating electron of its atom accommodated by one of the orbitals of 2p. sub-level, so hence its membership of the p block. So it belongs to p block because looking at the last energy level p shows that it belongs to the p block. So always check the last, so meaning that the last aspect of electronic configuration really matters. It will tell us the period, it will also tell us the group when we add it together with s. So then it will also tell us if it is p block when we see the letter p, and so on. Now let's take the last question, which is L. So from our L, they said from what we have, hydrogen is in a group of its own because it does not fit properly into any of the groups. Is it true that hydrogen has its own special group? So from the answer here, we can see that hydrogen, it is true. Yes, that means it belongs to its own group. Hydrogen 1s1 cannot be a member of the group 1a element, so we can't actually say it belongs to group 1. We only put it there because it also has valency of 1, just as other alkali metals. So, and because it is also a non-metal, so that's why we cannot just say it belongs to group 1. So it's a non-metal, but those elements in group 1 are actually metals, and hence not a base former. It doesn't form base, so it cannot be a alkali metals, though it can gain 1 electron just as other, so to attain the noble gas structure, filled orbitals in the outer shell. So yet it does not fit into the halogen group. So it means there are different places we would have put hydrogen. We can try to put it under group 1 because of the valency of 1. We can put it under group 7 because it can absorb 1 electron to complete its shell, just like the group 7 element. So telling us that it does not fit into a specific group. So that is where we are going to stop for today. So today we have looked at periodic table, the definition, the history, and the table also itself, what you can use it to produce. So thanks for listening. Once again, my name is Damilare.